To Hoboken headquarters. This is our main lab where we're building our quantum prototypes, AI photonic prototypes, and also test some of the very upcoming products. This is, as you can see, all of these are bulky on optical table. So our optical scientists building out verify the proof of concept on optical table, integrate with a lot of fast electronic that you can see around here, that drivers control our laser, single photon detector, and also fast electronic to help with encoding and decoding using digital to analog converter and analog to digital converter. All of these, what you see in here, will eventually migrate to a more simpler version that get into our rack mount quantum products. And our lab in our Fab 1 in Arizona, absorbing this kind of design and map that into nanophotonics. From there, we're building our practical, scalable, room temperature quantum system. So you're looking at our quantum network solution where we basically have two nodes and one entanglement source. This system not only perform quantum key distribution, but also perform quantum identity authentication. And you can see that all of the system are on optical table right now. The main core that we developed is our spontaneous Dow parametric conversion, which is a nonlinear waveguide that help us produce entangled photon that currently free space in this small optical system. And then we distribute our entangled photon into two nodes. You can see this is our InGaAs single photon detector, Alice and Bob, and they, translate the information, map into key to distribute key for encryption. And at the same time, people can basically input their identity, and we map that into measurement basis and detect with the same exact hardware to perform quantum authentication. The system looks bulky right now, but they should be able to fit all in 2 to 3 U rack mount system, which is very compact and room temperature. You don't see it here, but all of our optical system is inside this black box. We try to black out the optical system to block from all the ambient light or any sort of the light that we don't want into the optical box. And all of these are control electronic. You see the fastest digital to analog converter and fastest digital analog to digital converter, both over here to encode and decode information. The main core of our optical system is basically an optical feedback system where you map your complex computation into the physical evolution of the system. Over there, we have a few of our engineers are testing a working system. They develop further on the control and mapping of the problem to be more precise, and at the same time building the software stack so we can have an easy integrate with all the computational pipeline. Now you're gonna get to see all the labs that cover our manufacturing side and also nanophotonic chip testing. We basically take our nanophotonic chip, sometimes even without packaging, to test their functional and performance at our nanofabrication testing lab, and at the same time building our products, building prototypes, assemble them, test them in our mechanical and manufacturing lab.
Hi, I'm Cesar Martinez. I'm the engineering hardware manager, and we are part of the engineering team in QCI, where we build quantum computers in all around the spectrum, from LiDAR to optical LiDARs to quantum communications, cybersecurity, computers, entropy, and reservoirs. What you can see here is a couple of the computer PCBs that we designed that are part of the different systems that we have in the multiple products that we have. And my team focused basically in designing these PCBs all the way from choosing parts to putting them together, validate them, and get them working. And I basically focus in more in the system level engineering and guiding from the concept of all these PCBs to how you need to test them and how you need to integrate them. One of the boards that they have been for a long time for us, basically having a couple of products, have multiple functionalities. We use a lot of FPGAs. This has a not a very high-end FPGA, but we use it extensively, mostly for prototyping. In general, it's a well-known platform, and it's easy to develop on us initially. And then for example, we have here comparators that we use also for prototyping. This is another board that we use for prototyping. Basically, it's a delay line that we design in-house to do some validation. And this is part of one of our products that is present in the entropy quantum computers. Okay, what you can see here is mostly, is schematics in this side. It's basically pointing out to all the components of block components that are ICs, resistors, capacitors, and all the stuff that we put in the PCBs and are part of the system, subsystems. And what you see here on the right is basically all those components that you have in there, and they are put together with the routing and properly connections between one to each other. There's always a challenge to go from here to here. Mostly this is, you need to have a lot of be careful in what you're doing and be aware of what are the connections, what are the voltage levels, what is the functionality of those ICs. Learn each of these blocks works properly, and make them work with the neighbors around. And basically, and here you have all the components that once they are putting them together and you are almost happy with them, you start doing the routing, that is basically the electrical connections from one to another one. Well, that's basically what is going on here at QCI. Hopefully, you have a quick grasp of what we are developing in QCI, and looking forward to put these devices in a million of people, billions of people. Thank you.
Hey guys, I'm Pranav, manager for product design and manufacturing here at QCI. And my role here at QCI is basically take all the quantum technologies which is in R&D stage or concept stage and just bring it into reality. So that's what our product design and manufacturing team do, is take the design that scientists develop, see if we can make the product out of it, create the detailed designs, enclosures, manufacture it, and then basically ship it to customers. You're looking at here the mechanical lab space here at QCI. What you are seeing on the background is we have a lot of workstations, and you'll also see one of our mechanical engineer Jared here. What we do is a lot of the prototyping happens in this lab. So we have a lot of equipments, including like 3D printers, laser cutters, drill press, just to quickly make those prototypes. And we also manage a lot of shipping of the products from this space. So I'll probably let Jared take over a little bit and explain what are the challenges that he faces day to day, and then how he resolves them.
Yeah, thanks, Pranav. So, hi, I'm Jared, a mechanical engineer here at QCI. We face lots of problems day to day. Anything from tackling how to deal with the heat coming off of components and the calculations that go into solving for that, or even just trying to troubleshoot through how to take some of these really sensitive quantum photonics and put them into a real world environment. And, so that we go into the detailed research and kind of troubleshoot and do a lot of prototyping and rapid prototyping to solve that problem.
So right now you are in like mechanical working space, or what we call here as like the small machining room. What we have here is not a lot of, but one 3D printer, drill press, laser engravers. And what we do is we usually make rapid prototypes as soon as we design something to actually put it in the product and test it. So a lot of our engineers gets an opportunity to actually move faster in their product development cycle, rather than waiting for manufacturers to send the parts and then wait for like 2 weeks or something. Here you can just design your part, print it here, and then test it in your product. Jared is very experienced in using this equipment, so he'll explain you more about how he uses it on day-to-day basis.
Yeah, so with things like the 3D printer, we're able to fail fast. We're able to use a rapid prototyping and go through many different iterations of a product or of a bracket or something, which helps us move forward really fast. Things like the drill press, we're able to make some modifications or manufacture even small parts on. And here we have the laser engraver and a soldering station. And with this, we're able to actually do some work, whether it's wiring up a quick prototype or laser engraving our branding on a new product. So it's great to have these tools. We're able to work really quickly. And like Pranav said, rather than having to wait for manufacturers to produce something, we could test it out before we make that commitment.
Thank you for joining the virtual tour here at QCI in our mechanical lab space. I hope you guys learned something and excited to join the QCI in future.
Hi everyone, here's Helen. I'm a senior scientist here at QCI. So at QCI, my work mainly focus on researching and designing the quantum photonic system, and work closely with the team to transfer those concepts from beginning to the prototype, and then finally go to the production. We introduce one of our prototype device. We call it symmetry. So in symmetry, we have three components. So one is entanglement source. Here are two entanglement source. Another two, we call it quantum measurement module. So in the entanglement source, we will generate the photon pairs among the whole C band. And for one pair, we will use a spectrum filter to filter out this photon pair, and then traveling through the fiber link, going to the two users. I'll call it two nodes here. We usually call Alex and Bob. So both Alex and Bob will hold one individual measurement module to do the timing measurement. Here I want to introduce one of our device in our research team, which is SNSPD, the superconducting nanowire single photon detector. So this detector is very sensitive, because it utilizes the nanometer scale wires and cooling down close to absolute zero, about 2 to 3 Kelvin. So when the photon hitting this nanowire, it will break the superconducting events locally and generate some tiny electrical signal. By collecting those signal, we will know when the photon arrive, and with very precise timing and very sensitivity. So the sensitivity can achieve about 90% detection efficiency, and the timing is about 10 to 15 picosecond. It's really good. So this will help us to do a lot fundamental physics study, and during our research on the quantum communication, sometimes we need to deal with the very, very weak signal, even single photons. So this detector will tell us exactly when the photon being there and the timing information. So it will be good for us to do the proof of concept demonstration. Thank you.
Hi there, I'm Andrew Rotano. I'm a lab manager here at QCI Hoboken, and on behalf of Miles Marshall and Rachel Smith and everyone behind the scenes, I want to thank you for joining us on this lab tour. A few of the things you've seen today are our commercial products, which include quantum encryption, photonic optimization, other information processing forms, quantum sensors, and I hope we've demonstrated it takes a large number of STEM fields to produce these things, from electrical engineers, optics engineers, thermal engineers, mechanical engineers, down to the business operations, so procurement, logistics, shipping, all these things it takes to create a quantum company. And so thank you very much for joining us today. Please keep an eye on our socials for more information. You can apply for an internship or a job if you see one opening, and we'll send it back to the Q&A. Thank you. Bye.